Swayam Prabha. Digital India. Educated India.
Yeah, it's not the most general way. So dislocations initially were a theoretical concept. It was observed only 30 years after it was initially proposed theoretically. And so among the fathers of dislocations, there's this Italian guy, Volterra. And so what he said to create a dislocation is you start from, you have your elastic body, and then you take a magic knife, you go into your body, and with your magic knife, you make a cut along a surface. So you have created a surface inside your material with your magic knife. Then you displace the two surfaces by some amount, by a given vector. And so that vector can be either parallel to the surface, it can be perpendicular, it can be in any direction. So it can even be either positive like this, or it can also go inside. Then, so if you have created a void by the displacement, you fill it with new material. If you have overlapping material, you remove the overlapping part. Okay, so that after that, you now again have a continuous medium, but with surfaces. Now you come with your magic glue, you glue back the surfaces, and you let the system relax. What is, in that procedure, what is the dislocation? Where is the dislocation? Yeah, it's rather, so that's what I said. So I said, I take a surface here, then I move, so it means that I change the displacement. So I have a face here that I will call S plus, a surface at the back that I will call S minus. Okay, the two surfaces. And when I have glued, so I have imposed the displacements and I have re-glued the system. So actually what I have is I have the displacement along S plus minus the displacement along S minus. This is equal to some given displacement. And it's a constant along the surface. And so for the Volterra dislocation, it's a constant along the surface, it's a vector, and that's what we call the Burger's vector. There are other types of dislocations where B does not need to be constant, but actually they don't exist in reality. So Burger's vector. Okay, but now in this process, where is the dislocation? Or what is the dislocation in this process? Corner or, yeah, at the boundary actually. So the dislocation is where the cut surface ends, right? And since it is the border of a 2D surface, it is necessarily a line, right? So the dislocation is the defect that borders a surface on which there is a discontinuity in displacements equal to a given vector. Now there's one question we haven't answered yet, is I said, okay, this face is S plus, that face is S minus. Why not S minus here and S plus there? I could do it too. So I have to decide where is the plus face and where is the minus face. To do that, what you need to do is you need to give a direction for the dislocation. So you need to give a sense, so in that direction, for example. And then you use what we call the start to finish right hand rule, which is that here I used a direct circulation around that vector. So I turn like this. So it means I have a circulation that goes like this. This is the start, this is the beginning, and the beginning is S minus, and the end is S plus. And then the jump between S plus and S minus is B. Why do I say that? I say that because I could do exactly the same dislocation, but now if I decide that I orient the dislocation in the opposite direction, just minus B, right? So this would be a plus B, This is a minus b, but it's the same dislocation, right? So the sign of the Burgers vector depends on the direction of the dislocation line. You change the direction of the dislocation line, you change the Burgers vector, but you don't change the dislocation itself. So and this is very often and more often I find in papers, authors do not tell you, they tell you, yeah, that's the Burgers vector of the dislocation, but they do not tell you what is the direction of the dislocation. And then you don't know actually if it's this or that, and that's not correct. So always give the direction of the dislocation. Okay, there are two consequences from that. So the first one, although we discussed it a little bit with Anand yesterday, but since the dislocation is the border of a cut surface, a dislocation cannot end in a material. Because the surface, I mean, you cannot cut a surface such that the border starts here and goes there, and then there's nothing behind. It's topologically impossible. So a dislocation cannot end inside a crystal. It can end on a surface, because here I can have a dislocation and a cut surface like this. This is fine. So I have two extremities here of the dislocation, but that's on the free surface. But it cannot end this is not possible inside the material. You see what I mean? Yes? So one, the dislocation cannot end inside. Two, the Burgers vector, since it is the slip displacement along the surface, the Burgers vector is constant along the dislocation. The Burgers vector cannot change along the dislocation. Sorry, so this one would be coming out of the board. This one is inside. Yeah, imagine a body like this, and this would come inside, but it's inside the body. This is in the bulk, this is inside the body, and this one would be a surface that cuts the surface of my potato. No, sorry, this is in 3 dimensions. Sorry, this would be, it would be something like this. So seen from above, it's this. If you look from here. If you look from above, in my drawing, sorry, maybe that wasn't clear. That for me is something in 3, it's when you see a loop in perspective. So this is in 3 dimensions, it would be something like this. So imagine, imagine we are in an elastic solid, right? And with my knife, I look at this surface here, I take my knife, and then I make a cut. So here, after I've cut inside my elastic body, I have 2 lips inside the body. So I've created, it's like I create a crack, a small crack inside the body. And then I move the 2 sides of the crack, either like this or like that. But so if for example, I do like this, and I do nothing else, then I've created a real crack. That's not what I want to do. I don't want to create a crack, I want to create a dislocation. So what Voltaire has said is if I've created empty space, then I can fill it. Everything is magical. So I can fill the empty space with new matter, so that it's a continuous medium. And same thing, if I move this surface negatively like this, then I have overlapping material. You see what I mean? I start like this, and this hand here goes down. So here I have some overlapping material, so I remove some of the material so that I don't have overlapping material. And then I glue. The easiest would be I'm here and I do this. I shear like that. So here I've created no extra material, and then so I shear like this and I glue again, right? And that the border of where I've applied this shear is the dislocation. So it's going to be in our case here, it's going to be a loop like this in 3 dimensions. Yes, it's clear for everybody? So you mean the extra plane, the extra half plane? Yeah. So this is okay. I can answer that now, and then we'll go. So. Maybe wait a little bit. I'll tell you. But you have an extra plane here, but actually you have an extra plane on the other side here. So the extra half plane, you have one extra half plane on top here if you do the shear, and then you have one extra half plane at the bottom. So it means that your initial plane here has been cut in two halves. I'll show you an illustration later on. If it's not clear, ask the question again. Okay. So this were the basics. I forgot to mention, so there are two Bibles in the dislocation field. The Hearth and Lothar book, and there's a new edition with Phil Anderson that helped rewriting this new edition. So this is one Bible, but it's rather mathematically involved. Very often we say that there are all the calculations you don't want to do yourself in that book. So mathematically involved, and then much simpler, more physically intuitive is this Introduction to Dislocations by Alan Bacon, which is very pedagogical and very nice, but it doesn't go as far as the other one in terms of elastic analysis of dislocations. Okay, so we've said that. We've said the start to finish right-hand rule. Now, very often, and in simulations also, we look at straight infinite dislocation. So what is a straight infinite dislocation? Well, to form a straight infinite dislocation, actually what you need to do is you need to have a cut surface. I'm going to call this the cut surface. So the cut surface has to be semi-infinite. So I've put limits here, there shouldn't be any limit. So if I have a cut surface, which is a half plane, then what borders the half plane is a straight infinite dislocation. So that's our straight dislocation. It still has a sense, and it has a Burgers vector. Yes, that's clear? Yeah, I'm going to go back to this later on. Now, there are different types of loops. So when it's closed like this, we call it a dislocation loop. When it's straight, we call it a straight dislocation. So there are different types of loops. We've already said it. So when the shear that I apply is parallel to the cut surface, then we call that a shear loop. When we create void and we add matter, since we have added matter, these are the equivalent of interstitials. We have more atoms, so this would be called an interstitial loop. And if we had to remove matter, these are vacancies. So this is a vacancy loop. So we have three types of loops. And for the straight dislocations, we have two extreme cases. One where the Burgers vector is perpendicular to the dislocation line in the glide plane. So these are two shear dislocations. So B is perpendicular to T. So that would be an edge dislocation. Or B is parallel to T. That would be what we call a screw dislocation. But then for a loop, you have everything, right? If I have a Burgers vector like this, there's a region here which is edge. At the back, it's edge also because it's almost perpendicular. Then parallel to B here and here, you have screw regions. But then in the middle, you are neither edge nor screw, so you are mixed. And the vast majority of the dislocations are mixed dislocations. They are neither, especially in FCC materials. BCC is different. In FCC, the dislocations are neither edge nor screw. They are all mixed dislocations. Right? These are just two extreme cases. Okay. Now, and then this is related to your question. So if you have understood what I said before, to create an edge dislocation, you can do it at least in two different ways with the Volterra solution. If I want to create a straight infinite edge dislocation, I can do it in two different ways. What are they? Yes? So that would be the equivalent of that, right? So I have a line here, and I have a half plane, which is here. I cut the half plane, and then I move so I have, if the sense is like this, S plus is on this side, S minus on that side, and so I do a shear here of the Burgers vector B like that in the plane. So that's method one. There's a second method to create exactly the same dislocation. So here, where would be the cut surface? So if you want to do it, so here I've taken a cut surface here, which is parallel to B. I could take another cut surface. Yes, so to do that, where would be the cut? So to create exactly the same dislocation. Yes, we cut, the other solution is a cut surface like this, or a cut surface which is vertical. And then what kind of displacement or what kind of displacement do I need to apply to create the same edge dislocation? You need to do this, right? So what kind of loop would that be if you do this? Yeah, or interstitial. If you separate the two surfaces and add material, that would be an interstitial loop. So actually, an edge dislocation, in terms of mechanics, is not necessarily a shear dislocation. It can also be an infinite interstitial loop, or an infinite vacancy loop. Everything is completely equivalent, right? It's clear, yeah? You always have dislocations in metals or in crystals in general, just because very often a crystal will grow around a screw dislocation. So we're going to go back to the drawings of a screw dislocation, but with a screw dislocation, you have a step on the surface. And so atoms will go on the step, and we let the crystal grow, but in the middle, there's a screw dislocation. So initially, even if you have never deformed your crystal, you will always have a minimum number of dislocations. And then these dislocations can serve as sources of other dislocations, and that's it. Yeah. So that's one easy source of dislocations. Okay, now, here we finished the last lecture by writing Navier's equation in terms of displacement field. Well, actually, you can solve the Navier equation with a boundary condition, which is a discontinuity of displacement along a surface. And that gives you, and then you can get an analytical solution for what is the displacement field around the dislocation due to this discontinuity. And the simplest expression is the one which is written here. It's for the screw dislocation. So typically what you do mathematically is you assume, and I've heard you several times talking about cylinders. So the cylinders are in principle not necessary, but they are useful in this case. So what I do is I take a cylindrical chunk of matter. I define a cut surface. So for example, this here would be the cut surface. So my dislocation line is going to be here. And now what I need to do is I need to apply displacement discontinuity. And we said that for a screw dislocation, the displacement has to be, or the Burgers vector is parallel. So I'm going to take one side and I'm going to move it parallel to this line. So either like this or like that, right? So for example, if I move it like this, after the deformation, what I'm going to get is something that is going to look like this. And the Burgers vector is will be here. That works, yeah? So that's the screw dislocation, and we were saying for the crystal growth, actually at this ledge here, if you have new atoms that come here, that will make this step here just turn around, and it's going to turn around the screw dislocation, and then you can have crystal growth around the dislocation. So this is a well-posed elastic problem. I want to solve Navier's equation with this jump in displacement. And the solution, the simplest way to express the solution is by using cylindrical coordinates. And what you see in the solution that you have is that you have displacements. So if I'm using, this would be Z, and then I have a cylindrical frame of reference. So I have an ER in this direction, E theta in that direction, EZ in that direction. The screw dislocation will create displacements only along Z. There's no other displacement. And the expression of the displacement, UZ, is so the Burgers vector. And then here, if I take a reference line parallel here, I can define an angle theta, like so. And so it's going to be B times this angle theta divided by 2 pi. So it means that if I am along the surface on this side, then theta is equal to minus pi. So here I'm going to get B times minus pi over 2 pi. So that's going to be minus B over 2. So I have minus B over 2 on this side. And then when I go on the other side, theta is plus pi. So it's plus B over 2. And so the difference between the two is B, the Burger's vector. So it's fine. It satisfies the boundary conditions, right? So that gives you the displacement. Once you know the displacement, then you can compute the strain and the stress, right? And they come out nicely here. So again, it's in cylindrical coordinates, but you have only one, or because of the symmetry, you have two non-zero terms for the strain, B over 4 pi r, and then you have only two terms for the stress, mu B over 2 pi r. And once you know the strains and the stresses, you can compute the energy. And as we said before, so the energy, because the dislocation is infinite along that direction, right? I have an integral, initially it's an integral over the volume, but everything is the same along L, so I can take out the integral along L. So the elastic energy will be, so we had our 1/2 of sigma double contracted with epsilon. Because of the z invariance, I have a L outside, so it's L over 2, and it's the integral over the surface here of the cylinder of sigma double contracted with epsilon, right? Now I know these expressions, I put them in, and what I get is that. So what I get is, and I guess you all know what is going to happen. What I show is that the energy is L over 2, L over 4 pi. Sorry, no, I have an L. I have mu B squared over 4 pi. And now I need to integrate dr over r. And that's where all the trouble comes in, because this integral, it diverges both towards 0 and towards infinity. So to get a well-defined energy, I have to use two cutoffs, not just one, but two, to have a log of r over r naught. So it means, as in the drawing, that I need to take out some central part around the dislocation with a distance r naught. And that region will be called the core region, right? And then I need to stop my integral at some large cutoff here. That will be capital R.
So what was basically the source of that blowing up at the zero?
It's because, so if you look at the displacements, they do not depend on R. So when you are very close and you are turning around, your displacements, the gradient are infinite, because you are still going from minus b over 2 to 2b over 2 over a very small perimeter. And so your gradients explode, and that gives you the singularity. Thank you. So this is the result of our calculation. This is the elastic energy per unit length now if I divide by L, and I have the log and I have the two cutoffs. So two things to remember. One, you have this divergence, and the other one is that the energy is proportional not to the Burger's vector, but to the Burger's vector squared, as you see in that expression. We'll see the consequence later on. So it means that if I'm looking at either the energy or the stresses, so the stress is inversely proportional to 1 over r, so it means that it diverges at short distance. So within the cutoff radius here, the stresses and the strains become infinite, and so they are too big to be accounted for by elasticity. So within the core region, we cannot apply elasticity theory. To reproduce the core region, we need an atomistic model, whether a brute force MD simulations or a Piles-Nabarro model or something that will put the atoms back into the crystal. We cannot use continuum elasticity to account for the core region. And then the other issue that we have is that because it's 1 over r, it's called a long-range interaction. It's like a Coulombic interaction, meaning that dislocations will, in principle, see one another even at infinite distances because they interact as with a 1 over r interaction. Now, what we do in practice is what we say is for the energy of the dislocation, we say that we have some elastic energy which is stored outside of the core, and then we add a term that cannot come from the elastic theory that tells us what is the core energy. So the total expression for the energy of a screw dislocation would be, so E would be some core energy plus, or E over L, if I do the energy per length, plus the mu B squared over 4 pi log of capital R over small r. Yes? So that would be the total. So we say outside of the core we have elasticity. Inside we have something that cannot come from elasticity. And we will see, I mean, I've put an input file with lamps, and I think at the end, if I have time, I'm not sure. But obviously this term here can come from atomistic calculations. To do that, what do? We build a screw dislocation inside a cylinder. We do calculations for different radii. And then we plot the energy as a function of the log of r. And then the slope will give us the shear modulus if we want to. And then the intersection with the vertical axis will give us the core radius. Now, note that if I change the value of R naught, because I don't know what R naught is. Usually we say it's 1B, but it can be 2B, 3B. We don't know what it is. If I change the value of R naught, I will change the value of E core. So the core energy is only defined if we know what is the core radius, right? And actually it can be negative. Depending on the value that we take here, we can have a negative core energy, which physically sounds weird, but it's just a mathematical consequence of the fact that what counts is E core plus this times the log of R naught, or minus the log of R naught.
Here the R naught is almost arbitrary, yeah?
Yes.
But we would like to keep it like around few atoms?
In practice, so it depends on the dislocation. If I have a compact core, like I've drawn here, usually 1B is enough. But there are some extended cores where you have to take more than just 1B. You'll see examples this afternoon in FCC crystals. Yeah, even so with nonlinear, you can gain a little bit, but there's still a point where it does not, it breaks down. Yeah, you really have to put in the atomistic nature of the material, like with a Peierls-Nabarro model, to get something that makes sense. Yeah, nonlinear elasticity doesn't work. Yeah, no. It's fine for the others. Yes. Okay. Now this is for the edge dislocation. I won't go into the details. It's basically the same except that it's more complicated. For the expressions of the stresses and the displacement and so on, the energy is not very different. There's just the 1 over 1 minus nu that differs from the screw dislocation. Otherwise, it's the same expression and same business of divergence. Now, mixed dislocation. So this has got both a good thing and a bad thing. So in every textbook, everybody talks about edge and screw dislocations. And so a lot of students think that there can only be edge and screw dislocations, which is, that's the bad side of it. The good side of it is that once I know the energy and the stress fields and so on of edge and screw dislocations, I know the displacement field, stress field of any dislocation because superposition theorem, because elasticity is linear. So if I have, if I take, that's the example which is here, but if I have a dislocation with a Burgers vector which is neither edge nor screw, I can always decompose this vector into an edge part and a screw part. And I know that the displacement field of the full dislocation will be the sum of the displacement field due to this guy plus that guy, stress field the same, etc., etc. Moreover, and that you have to show it, but moreover, if you look at the energy, actually a superposed screw and edge dislocation do not interact with one another. That integral of sigma times epsilon is 0 when you are looking at the energy at the energy of an edge and the screw. So there's no interaction between edge and screw. As a result, the energy of the full dislocation is also the sum of the energy of the edge plus the energy of the screw dislocation. Yes.
That is only when the line vectors are parallel.
Yes. Yeah, when they're not parallel, then they interact. Yeah. So along a dislocation, if it does that, then segments away will interact. But when they are on top of one another, there's no interaction. So everything is linear here, right? Yes. So that's why we only talk about edge and screw. But we have to keep in mind that most dislocations are neither an edge nor a screw. I have one dislocation here, which is formed of a Burgers vector, for example, like this one, B. And now with that Burgers vector, I can also, for example, take a vector like this, plus, or if I don't want to do edge and screw, a vector like this plus a vector like that. So I have a B1 here, and I have a B2 here. And so what we just said is that the full dislocation is just the sum of B1 and B2. Yes? So now let's assume that on one hand I have just a single dislocation with a B Burgers vector. And on the other side I have two dislocations. And I assume that they are very far away. One with the Burgers vector B1 and the other one with the Burgers vector B2. Right? So I have this system here, and I have that system there. What's the energy of these systems? The elastic energy stored in these systems due to the dislocation. Here, the energy which is due to this dislocation will be proportional to. So what we said is that the energy of a dislocation is proportional to B squared, right? So actually it's mu times B squared. So in this case, this would be mu, and then this would be B1 plus B2 squared. And so that's mu, and I have B1 squared plus B2 squared plus 2 times B1, B2. What is the energy of this system? This one is mu B1 squared because of this guy, plus mu B2 squared. So when is it energetically favorable for these two dislocations to join and form a single dislocation? If this term here is negative, then that energy is smaller than this one, and so the dislocations will gain energy by joining and forming a junction with a single Burgers vector, right? So you can extend that, and it qualitatively works. It's called Frank's rule. If I have two dislocations, if the dot product of their Burgers vectors is positive, they repel each other because they don't want to join. If the dot product is negative, then they attract each other because they want to form a junction, and that's called Frank's rule. And it comes just by the fact that the line energy is proportional to B squared. So I think it's what I have here. So we said the mix with the linearity, and then that's the Frank rule, and exactly the example that we said. Two dislocations attract each other. So it's a very approximate calculation, right? But in practice, I've never seen a case where it didn't apply, even if we've done the calculation in a very simple setting. Well, if it is equal, then it's the same whether they are on top of one another or if they are separated. It's the case of edge and screw. So if this is an edge and this is a screw dislocation, then one will be perpendicular, the other one will be like this. So the two Burgers vectors will be perpendicular. So the dot product will be 0. And so it will be the same energy whether the dislocations are far away or they are together. And that's because they are not interacting. So that's why, so since edge and screw dislocations do not interact, then there's no difference in energy. And so the rule also works in this case, right? And that's why I was confused earlier. It's clear? You'll see applications of that. If you want to understand dislocations in FCC materials, for example, you need to have this Frank rule in mind. Okay, and now that might answer also your question. So that was for dislocations in continuous medium, but we want to do atomistics, right? So let's move on and talk about start to talk about crystals. So if I have a crystal and I want to create a dislocation in that crystal, let's take a good old simple cubic unrealistic crystal. And I want to create an edge dislocation. I do the simplest thing I can do. So what do I do to create an edge dislocation? With, let's say, using a shear procedure. So let's do it with shear. It's easier with shear to see what is happening. So with shear, so I need to define a cut surface. So if I want my edge dislocation to be here, the cut surface will be, no, for shear, it's going to be something here. It's going to be horizontal. So here I cut with my magic knife. I cut the bonds, and then I move the top part with respect to the lower part by the Burger's vector. Now, if I use a small vector like just this, what is going to happen is that this atom, these two atoms will just be a little bit sheared. If I relax, the crystal is going to go back, right? So what is the smallest vector I can use as a Burger's vector? It's the spacing, because if I do that, then the atoms, so assume that I do not move what is at the bottom. This atom here, by the shear process, this atom here will go here. The atom that was here will come here. The atom that was here, well, this one does not move if I stop here. So this one, the atom that was here will come somewhere around here. And I do the same for these atoms here. So they move, and I have this atom here. They move, and I have the atom here. So in the end, so if I stopped here, the shape that I have is something with, there's a step now on the outside, which is equal to the Burger's vector. And then I have recreated my crystal, except that now I have some atoms here that stop. It does that. Now I relax the system, because so far it's not relaxed. So now I glue again the interatomic interactions, and I let the system relax. These planes here are very close, so they're going to expand. And so in the end, what I'm going to get is something that will look like this. Yes, so that's an edge dislocation, and as you I guess all know, it corresponds to an extra half plane that stops in the crystal, and the dislocation is perpendicular to the board. Yes? And the smallest vector I can use to create the dislocation is this one. Now, could I use two Burger's vectors to do the same? Or what would happen if I use two Burger's vectors? Two interatomic distances, I mean. Instead of shearing by one distance, if I do it with two distances, what is going to happen? So there's going to be two extra half planes. What will be the Burger's vector of that dislocation? It's going to be 2b. So what will be the energy of that dislocation? 4b squared. Now, if I assume that if I look at the dot product of b by b, it's always positive. So that 2b dislocation will be unstable with respect to dissociation. And so I'm going to go back to a Burger's vector, which is equal to the interatomic distance. So as a general rule, because the energy of the dislocation is proportional to b squared, the Burger's vectors that we find in crystals are always among the smallest vectors of the lattice. So the smallest is always included, and sometimes you have some of the slightly larger, but then quickly the energy becomes too big for the dislocation to be stable. Yes? So that's one thing I wanted to say. Then we have that. Yes. And so here, so the magic of a dislocation. So this dislocation, we call it a perfect dislocation because the Burger's vector is a vector of the lattice. And so when I move the atoms, I do not create any fault along the surface. So that's a perfect dislocation. And the magic with a perfect dislocation is that if I look anywhere except where I've put my hand, I have a perfect crystal except for some elastic deformation. All the big rearrangements occur here. And so this would be, that's the core region. So this section here is outside of elasticity. All the rest is inside elasticity. Now, many people, and us included, we have produced these dislocations at the atomic scale and compared the elastic displacements outside of some region. It compares extremely well with the predictions of the elastic theory. So the elastic theory works very, very well. Even if we started with a very unrealistic process to create the dislocation, in the end, we get something that is very realistic. So we have these perfect dislocations whose Burger's vector are among the smallest vectors of the lattice. So it means that FCC, the most common Burger's vector is half 110. BCC, HCP, yeah. Now you have some other vectors. No, it's here, sorry. So this is the most common. In BCC, you have the half 111. You also have the 100 sometimes. And in HCP, you have the A vector here, but you also have the C plus A dislocations. And what we call, so this is a perfect dislocation, and what we call a partial dislocation is when B is not a lattice vector. And so it means that you create a fault along the surface, you create a stacking fault, and that applies to FCC materials. We will talk about them later on. Now, with our cut process, if I want the dislocation to move in the crystal, but without needing either interstitials or vacancies, this can occur only if the dislocation moves in the plane which is perpendicular to the surface, to have just a shear process, right? So that's what I'm saying here. There is what we call a slip plane. So it's the plane in which the dislocation can glide without needing neither vacancies nor interstitials. And so again, it's less exact as a rule, but generally, these slip planes that we mostly see in crystals are among the densest planes of the system. So in FCC, it's going to be the 111 planes. Sometimes also we see 001. In BCC, well, BCC, it starts to be a bit ugly. We have the 110, which is the densest we discussed yesterday. But we also see 112 and even sometimes 123. And then in HCP, well, HCP is the bad guy, so you have everything. You have basal, prismatic, pyramidal 1, pyramidal 2, no, sorry, pyramidal here, pyramidal C plus A1, C plus A2. A mess, as always. That's fine? And now, just for the terminology, what we call a slip system is the combination of a Burger's vector and a slip plane. So for example, in FCC crystals, the most classical slip systems that we see are a Burger's vector 1/2 of 110 and a glide plane 111. So that's the slip system, and there are 12 of these slip systems in FCC crystals. Okay, so that was for the generalities on dislocations. Now I want to talk about what you're going to do this afternoon, which is model at the atomic scale a dislocation. Here you have 3 different options, and they all have their pros and cons. So the first one that was used historically is just translating this into an atomistic model. So what you do is you create, so if we look at how it works, you start by creating a perfect crystal. Then you use, for example, if you want to create an edge dislocation by a shear process, you move all of the atoms using the elastic displacement field that gives you from the elasticity theory. So I should, for pedagogical reason, I should have given you the expression, but it would be this, the straight field that you get here. So the main term is same as a screw dislocation, but there are other terms because edge is always more complicated, right? But I know this stress field, this displacement field from elasticity, and so I just displace the atoms using this displacement field. It's not the exact displacement field, but I don't really care because of something I'm going to talk about later on. So go back here. I create a perfect crystal. I move all of the atoms, and so now I've created a step on the surface here. Now what I do is I define the cylinder, and I remove all of the atoms that are outside the cylinder. So I've created a cylinder with a dislocation in the middle. And then if I don't want the dislocation to move away, what I do is in this cylinder, I define an outer region here where I fix the position of the atoms at their initial positions. And then I do an energy minimization for the atoms that are inside this mobile region here, keeping the atoms outside fixed. Why is that? What do you think? If I didn't fix the atoms on the outside, what would happen? Yeah, the dislocation will just go away because you have free surfaces everywhere. Dislocation costs a lot of energy. So if the crystal can get rid of the dislocation, it will, definitely. So if it's free surfaces, it's going to go away. and then you're in a bad situation. So you fix the atoms.
Even after fixing the surface atoms, dislocation can have the image force and it can move towards the surface.
Yes, but so if the dislocation, now if you have fixed atoms here, if the dislocation wants to move in this direction, then the dislocation, to remain at equilibrium, these atoms should also move. They should relax. But since they cannot, that will create a repulsive force on the dislocation. You see, yeah? So actually, if I have free surfaces, the dislocation is attracted by all the different sides because it will disappear. If it's fixed boundary conditions, then it is repelled by all the sides, and so it's going to stay in the middle.
So what about the z direction? Is it a periodic?
Sorry, yeah, I forgot to mention. In this simple case, we use periodic boundary conditions in this direction so that we have an infinite straight dislocation. Yes, that works. It's clear. So this is historically the first method that was used, and actually we used it. So there's if you want some references about how to create a simulation and so on, some years back with Yuri Osetsky and David Bacon, we wrote a chapter in dislocations in solids where we give all the gory details about these simulation cells and so on. Anyway, so more recently, I'm going to jump forward here. Yes. So more recently, so now 6 years ago already, with Bill Curtin, we applied this method. I mean, other people had done it, but we had another thing in mind. This was just one part of the study we did, but we end up using exactly the same methodology to compute the core energy. And so what I said is, so we used, we assumed a core radius of 1 Burger's vector. Then we varied the outer radius from something around 1, so very, very small simulation cell, to several hundred Burger's vectors here. And then for different dislocations, so you see here it's in nickel, so it's an FCC metal, and it's modeled with the machine potential. I showed the paper yesterday, so you see something very classical. And this is the energy inside the cylinder. We don't want to compute the energy of the outer atoms because this would be influenced by the surface. So we compute only the energy inside. So this is the energy as a function of the radius, of the log of the radius. It's in log scale. And what you see is that if you are far away, you have something which is nicely linear, as the theory says. And if you go back, so now if you go to small sizes, then you have strong variations. And that's because the surfaces start to interact with the core, and also because we are getting inside the core region. So here we have deviations, but we don't really care about these deviations. What we care about is the intersection here with the axis with when r is equal to b, and that gives us the core radius. Yes? Okay, so that was option number one. Option number two is to use what we call a periodic array of dislocations. So here the idea is the following. You start with, so there are different ways to implement it, but historically what we did was you start with a dislocation with a step like this, and then you apply the displacement field, the elastic displacement field of an edge dislocation to that structure. What is going to happen is that, so with the displacement field, the top part will be displaced by B compared to the bottom part. So that actually will remove the step on the outside, right? So what you're going to get is now a simulation cell. It's not nice. I mean, the surfaces here are a bit deformed, but there are no longer any steps. And on average, the size of the cell is going to be L. So if this was L plus B, after introduction of the dislocation, the cell has a size which is close to L plus B over 2. And now these two sides, they are almost vertical. So what you can do is you can apply periodic boundary conditions to this cell with a length of L plus B over 2. So now you add periodic images. And so initially there will be energies on the sides here. But if you do an energy minimization, the planes very nicely will go back, become straight. And what you have created is an infinite array of parallel edge dislocations. So you have periodic boundary conditions here. Along the line, you also have periodic boundary conditions. So you have an infinite plane. Now, on this side, you have the extra half plane. And on that side, you don't. So you have more vertical planes on this side than on that side. So you cannot apply periodic boundary conditions from top to bottom. So different groups have done different things. What we do is simply we let the atoms, we have free surfaces, top and bottom.
But in that case, you have to freeze the top or bottom.
So it depends on what you are doing. You don't need to. So if you do that and you just let it free, the dislocation, if it's an edge dislocation, the edge dislocation can only move along that plane. So it's gonna stay actually where it is. It's not gonna go to the free surfaces.
Not about that dislocation, but about the atom and the surface.
If it's a free surface, I mean the atoms. So the atoms will see that there's a free surface. They will relax, but nothing else will happen.
Yeah, I did some amount of vacuum on the.
Yes, so what you do in LAMPS is either you keep boundary conditions, but you have some free space, or in the boundary conditions, you have this FM, instead of P, you put FM, and that will put an infinite system. So they remove the boundary conditions in the corresponding direction. You'll see this afternoon. And you will see this afternoon, you will relax a dislocation, and you will see that the surfaces are not a problem. That works? Yes? So the good thing here is that because we have periodic boundary conditions, and we'll see that later on, but we can also apply a stress or a strain on that system. We can shear the system. We can put the dislocation in motion, and since it's periodic, the dislocation will go here and then come back here, and actually it can turn around the simulation cell infinitely. And so that allows us, for example, to measure the velocity of the dislocation as a function of the applied stress or the temperature and so on. So that's the good thing about that. The bad thing is that the dislocation here will interact with its periodic images. And we know that the interaction is long-ranged, so we know that there will be effects. So in particular, so for example, if you put a defect inside and you force the dislocation to interact with the defect, the dislocation will bow out, and we know that the bowing out will be limited by the interaction with the periodic images. It's always smaller than what it should be. Another artifact, but I don't want to talk about it. Is it clear? So that's the pad, and so that's what you're going to use this afternoon. It's this pad geometry. These are longer simulations, so you won't have enough time, but imagine that I create a cell And then I use the pad, so I have periodic boundary conditions here, and then here and here. I create an edge dislocation here. And then in front of the dislocation, somewhere here, I put a precipitate, for example, or an irradiation defect, a loop. And then, I don't want to go into that today, but imagine that I shear the system. The edge dislocation will move, will come in contact, and then it's gonna do something like this. This part being connected to that part, but then it's gonna bow out in between. Because now with the periodic boundary conditions, actually what you have is not one precipitate, you have one here, but then you have periodic images of the same defect, and so the dislocation actually will bow out between the defects. And if you increase the stress until the dislocation goes away, you can measure what is the deepening stress of the dislocation from that defect. That was the motivation for developing these boundary conditions. So yes, so it's periodic here. From here to here, it's periodic, and from there to there. So because of the periodicity here, what you have is an infinite dislocation. And because of the periodicity here, you have an infinite glide plane. Infinite but periodic. So it means that in your simulation, for example, if it's a precipitate, the dislocation goes through, it's going to shear the precipitate. Then it's going to go here, it's going to come back, and then it can shear the precipitate again. And so induce a double step, then a third step, etc., etc. So the artifacts are coming mostly from the periodicity in this direction here. Because this dislocation here, ahead of it, there's another dislocation doing the same. And so you have two parallel dislocations with the same Burgers vector. That's the worst case scenario for interactions. And so what we have seen is that if I have my two obstacles and the dislocation is bowing like this in my simulation, if I make the simulation bigger and bigger and bigger to decrease the interactions, what I see is that the bowing out will increase. And will increase more and more. I mean, at some point it will stop. But I know that the bowing out will increase if I make the simulation cell bigger and bigger. And that's because of the interactions between the two dislocations, between the infinite number of dislocations. Dislocation dynamics, you need parameters. You need a core energy or a line tension. You need a pinning stress. You need to put in numbers that can only come from the atomic scale. So for sure, once you have given all these numbers, and with Bill, we have worked on that, and that was part of the work. So we computed the core energy in part to show how to calibrate dislocation dynamics from atomistics. If you do the calibration correctly, your dislocation dynamics calculation will reproduce exactly the atomistic, and then you can put many dislocations and look at more complex interactions. With MD, we will always be limited to one, maybe two dislocations at most, whereas with DD, you can go to much larger. So it's the same as when you go from DFT to interatomic potentials. You can do such that the interatomic potential will reproduce exactly the DFT on small cells. Then you can do bigger cells, but you know that it's not going to be as accurate as the initial DFT. So it's same philosophy between MD and DD. But when you look at this size effect on the yield stress, actually, yeah, you can see that it converges, and then you can either say, well, yeah, I'm sufficiently converged, or you can do an extrapolation and try to do a prediction, but it's going to be there. So that was for the edge dislocation. Now the screw dislocation is a bit more tricky. So this is where we're going to see if you understand what a screw dislocation is. So I want to do the same. I want to have a cell, and in the middle I want to have a screw dislocation, not an edge. Now imagine what we're going to do is we're going to look at the glide plane of the dislocation. So this is the glide plane. And so here now the screw dislocation is here. Now imagine I look at a plane, a vertical plane. So which initially that plane, so the dislocation actually, or the crystal would have a series of these vertical planes like this. You see what I'm doing? So we are looking from the top at vertical planes like that in the crystal, and we have the screw dislocation, which would be here. So for example, if we are in BCC, the Burgers vector here will be a 1, 1, 1 Burgers vector, a third of 1, 1, 1. And so these planes would be, it's the same indices. So since everything is perpendicular, so this would be 1, 1, 1 planes, right? So this is before I introduce the dislocation. Now, after I have introduced the dislocation, what happens to these planes? So what is the displacement? What did we say about the displacement field? For the screw dislocation, if I have, so if the line is in this direction, I turn around like this, right? So positive sense, start to finish. And so the displacement in this region will be minus b over 2. The displacement in this region will be plus b over 2. The displacement in this region will be 0. Yes? So now if I look from the top, so this region here would be here. So actually these planes will not change. Now if I'm looking behind, and if I am looking at the top part of the plane behind, what happens to that plane? It's going to be shifted by b over 2. So it's going to be somewhere here, right? And as I go towards the core, it's going to go to 0 like this. Now if I look at the plane below, what happens to it? Minus. So it's going to do the same. So that's for this plane. For this one, I do the same. This one is going to do this. And then the next one will do this. You see what I'm doing? Now if I want to apply periodic boundary conditions, what can I do? So I want to have periodic boundary conditions from here to here. So I want to connect an atom which is here with a neighbor on the other side. With which neighbor do you think I can connect that atom? So actually, I can choose. Either I can connect it with that atom or the one above. If I connect this atom to that atom, so I connect this atom to that atom, this one to that one, this one to that one. Now, on the z direction, along the dislocation, you agree that it's still periodic, there's no issues, right? So no issues in this direction. Now here, I need to connect here to here. So what does it mean for the periodic boundary conditions? Or what does it mean for the simulation cell with this type of boundary condition? So if the periodicity is from here to here, actually the simulation cell is no longer orthorhombic. It has a tilt. Or I would need one more atom here. No, it's here. If I define a simulation cell like so, so it should be, sorry, this one should be at the middle here. This one is at the middle. Yeah, it's at the middle here. If I apply periodic boundary conditions to a cell which has a tilt like this, then this atom here, when it leaves, it's going to come back down here. When this one leaves, it's going to come back here. When this one leaves, it's going to come back here. And so I've connected this side of the plane with that side of the plane. So what we do for screw dislocations is we apply periodic boundary conditions, but in a cell which is tilted, and the distance here is b over 2. You see what I'm doing? more or less. So this shift equal to b over 2, this is true only when we are exactly along the glide plane. When we move away from the glide plane, the shift isn't exactly b over 2. So it means that at the beginning, the planes are not fully aligned, but we do an energy minimization, and they nicely realign, and I have a screw dislocation with periodic boundary conditions left to right. And then front to back very easily, and I keep free surfaces top and bottom. Do you see? Yeah, we have. I'm not sure I have. So, no, yes, there is an example, but for BCC dislocations, not today. Today it's only edge, but there's an example on tomorrow maybe. Yeah, day 3, with a screw dislocation, and you can look at the simulation cell, and you see that I've added a shift of b over 2 for the screw dislocation to reconnect the boundary conditions. Yes? So that's what I tried to illustrate here. Not very good, but anyway, I hope you understand that. Yeah, it's clear. Do you have questions or not? You see how it works? And actually on that graph, I need to change that graph because I forgot to put the plane below. So I'll change it. Now there's a third option. If you really want to use periodic boundary conditions. So like, for example, if you are doing DFT, with DFT, you don't like free surfaces because your simulation cells are so small that if you put a free surface, wow, it's going to explode. So you really want to use periodic boundary conditions because they limit the size effect, as we said earlier. So there's one way to have 3-dimensional periodic boundary conditions. And this is what? How do you do that? How can you have dislocations or a dislocation with fully periodic boundary conditions? So you can put a loop, but same thing in DFT, we don't have enough atoms to make loops. If I want to make an infinite dislocation, but I want my system to be fully periodic. No, so vacuum would kill the DFT calculation. Yeah, actually, no, that does not work. No. What you do is you don't put one dislocation, you put, it's a bit of like a loop, but for infinite dislocations. You put 2 dislocations. You make a dislocation dipole. Because if you have, so you create 2 dislocations with opposite Burgers vectors. Then these 2, if they have opposite Burgers vectors, the total Burgers vector is 0, and so you can apply periodic boundary conditions everywhere. The price to pay is that now in your simulation cell, you don't have just one, you have 2 dislocations. And so basically you spend half of your time calculating something that you don't care about because everything you care is only on one dislocation and not on the other one. But that's the price to pay. So this is the idea. So what you want to do to minimize the interaction between these dislocations is you want to make a square array of dislocations with alternating Burgers vectors, plus b minus b, plus b minus b like this. So you have 2 choices. Either you use a non-orthorhombic cell, like this one, where you put only 2 dislocations. Or if computing time is not really the issue, you can keep an orthorhombic cell, but now you need to put 4 dislocations in your simulation cell. But the good thing is, as I said, now you're periodic everywhere. You see the idea? So for those who will come to the talk my talk this afternoon, when we do DFT, this is the cell that we use because we don't want to have the free surfaces. So in DFT, several of our PhD students lived with 135 atoms. The cell is 135 atoms, and we put 2 dislocations in that crazy small cell. So we know that if we have this very small, I can show you. So this is in a BCC crystal. This is a 1-1-1 direction. And so each circle here is an atom. So you can count them. There's 135 atoms. And in that small cell, we have put a dipole of dislocations. There's 1 screw dislocation here, and there's another screw dislocation there. And two of our PhD students spend their entire PhD doing simulations for 135 atoms, because that was the biggest we could afford at that time. So it's crazy because the dislocations here, they are extremely close to one another. So we know that these two dislocations will strongly interact, but they will also strongly interact with all of their periodic images, right? But then my colleague and friend Emmanuel Clouet, he has spent a lot of time working in elasticity. So he went to anisotropic elasticity to be more quantitative, and he has shown that actually, so when we compute the energy of this cell, then we can also compute what is the elastic energy that corresponds to the interaction between these dislocations. So we can take the DFT energy, we subtract the elastic energy, and then we get a number. That number actually does not depend on the cell size, or very little. So once we have taken out all of the elastic interactions, the numbers that are related to the core energy of these dislocations, they no longer depend on the cell size. And so most of what we have done at DFT is that we use periodic boundary conditions plus these elastic interactions to remove the size effects. And the numbers that we get are, for all the tests we've done, they are as quantitative as they can be. But that's how we do. So that's how we do DFT. When we do MD, we use PAD. Usually, it depends on the systems. Same thing. If you are looking not at a metal but at an ionic system, with an ionic system, so you have an example for tomorrow if you want to look at it, which is dioxide uranium. In an ionic system, if I use PAD, then on top and bottom here, I'm going to create charged surfaces. And that's bad for the calculation. So with ionic systems, it's much better to use a dipole, because then you don't have these free surfaces. So depending on what you want to do, you can choose either one of the three options. And I think I had this, so, and then we're going to finish on that. So just to say that they, as I said, they have all their pros and cons. So this one here, the pros is it's directly connected to elasticity theory to compute a core energy, for example. Then you can somehow a little relax the fixed boundary conditions using Green's function. So we haven't really talked about Green's function, but there was some years back, maybe, I don't know, 15 years back, there was a lot of activity in using Green's function on the outside to let the atoms move as the dislocation is moving. It had some success and also some big failures. So nowadays, no one uses that anymore, to my knowledge. Maybe I'm wrong, but I don't know anyone who's still using that. The bad thing is that, as we said, if the dislocation moves, it's going to strongly interact with the atoms on the outside, and there will be image forces on the dislocation. So this is well adapted if the dislocation does not move and stays at the center of the cell. The pad here, so what is nice is that it works whether the dislocation stays or moves in the simulation cell. And we haven't talked about it, but it can be used by applying either a stress or a strain rate on the surfaces. So that's nice. The bad thing are all the artifacts due to the periodic boundary conditions and the geometry that we were not able to express analytically to correct for them. So they are there, and we don't know exactly what is their amplitude. So the only thing we can do is just change the cell size and see what changes. And then we have these charged surfaces with ionic crystals. This one, what is nice is there are no image forces, no free surfaces, and as we have said, it can be used with DFT. The bad thing is that it does not work for moving dislocations, because if the dislocations move, they're going to annihilate. So they cannot move either. It's like here. And the bad thing also is that you spend half or 3/4 of your time modeling dislocations you don't care about, because you only care about one of these dislocations. So there's a lot of wasted computational time. If you apply a stress, it does not work. Now, if you compute the Peierls barrier, then the Peierls barrier is computed with no applied stress. And what you can do is just look at the energy when both dislocations are moving together. Then they stay at the same distance, and then you're fine. Then there's no artifact. But you have to move all of the dislocations together.